Good morning, my dear friends. I hope you all are doing great. Dear friends, today we'll be talking about characteristics of equilibrium constant, and that equilibrium constant is our Kc. Okay? So the first point here is equilibrium constant can be calculated only when reversible reaction attains equilibrium. So value of Kc can be only calculated at equilibrium. That's it. So have a look. If you have a chemical reaction, A plus B gives me C plus D. This is my chemical reaction. Okay? So this is only a forward reaction. This is a forward reaction. So here I can't calculate the Kc value for this because this reaction has not reached equilibrium. But if I take the reaction like A plus B reacts to give me C plus D, and C plus D interact with each other and give back A plus B. That means it is both forward, okay, it has a forward direction as well as backward direction. A plus B gives me C plus D is a forward reaction. C plus D will react to give me A plus B, that is a backward reaction. So this reaction has reached to equilibrium, because rate of forward reaction for this case is equal to rate of backward reaction, my dear friends. So that means here I can calculate the Kc value. So Kc value can be calculated for this reaction but not for this reaction, because this is just only a forward reaction. This reaction has not reached equilibrium. Yes or no? So it is only a forward reaction. A plus B gives me C plus D. But this reaction is a reversible reaction, where reactants are changing into products and products are changing back into reactants. So we will say that this reaction is at equilibrium. And now I can calculate the value of Kc. And you know how to calculate the value of Kc. Kc is equal to molar concentration of products divided by molar concentration of reactants raised to the power equal to their stoichiometric coefficients. So here Kc value will be calculated, but not for this. Let's go further and understand the point second. Let's have a look, my dear friends. Catalyst does not change Kc value. Equilibrium constant value is not affected by the catalyst. Yes? Because catalyst speeds up forward and backward reaction equally. So let's take, first of all, let us understand what is the role of catalyst. Okay? There are two types of catalysts, positive catalyst and negative catalyst. Positive catalyst will increase the rate of reaction and negative catalyst will decrease the rate of reaction. Let us talk about positive catalyst here. Okay? So when we talk of a positive catalyst, my dear friends, okay, let's talk about a positive catalyst. Okay? Positive catalyst, it speeds up or increases, you can say. It speeds up or you can say increases rate of reaction. So role of catalyst is to increase the rate of reaction if it is a positive catalyst, correct? So what is my point here? Look here. Catalyst does not change Kc value. That means Kc value remains unaffected. Why? Because catalyst speeds up forward and backward reaction equally. That means if you are using a catalyst, let us suppose I will take one chemical reaction here. A plus B gives me C plus D. For this reaction, it's in forward direction and backward direction. So rate of forward reaction is equal to rate of backward reaction. Yes or no? So for this thing, this reaction is at equilibrium, my dear friends. So here I can take the Kc value. Kc value will be molar concentration of products divided by the molar concentration of reactants. Let's take on some stoichiometric coefficients A, B, small c, small d. So let's take a look at small c, d, A and B. These are the stoichiometric coefficients. So this is the Kc value. What I am going to do, my dear friends, I am going to put the catalyst, this catalyst, positive catalyst I am going to bring. If I put a catalyst here, so what will be the role of this catalyst? Okay? What is happening if I don't put the catalyst? Rate of forward reaction is equal to rate of backward reaction, correct? Yes? In absence of catalyst. But in presence of catalyst also rate of forward reaction will become equal to rate of backward reaction. Because the catalyst will increase the rate of forward reaction, okay, x times, and it will also increase the rate of backward reaction x times. That means it will increase the rate of forward reaction and backward reaction equally. So when the forward and backward reaction are increased equally, then understand that Kc value will not change, my dear friends. So what is my point? Rate of forward reaction is equal to rate of backward reaction, okay, when there was no catalyst. But then I put a catalyst for this reaction. Once I put the catalyst, still the rate of forward reaction is equal to rate of backward reaction. But the only one thing has happened. The rate of forward reaction has increased x times. And rate of backward reaction has also increased x times. So total change is how much? 0. That means how much is the increase in speed for the forward reaction? That is the same is the increase in speed for the backward reaction. That means Rf will be equal to Rb, and this value will also remain the same. Yes or no? Kc value will also remain the same. Kc value depends upon molar concentration of products divided by molar concentration of reactants. Yes? If you think that more product will be formed, yes, then the product will change back into reactant. That means more reactant will be also formed. Yes? Because speed is increasing x times in forward direction and x times in backward direction because of catalyst. So if more product is formed, then in reverse more reactant will be also formed. More product, more reactant. Yes or no? So overall this ratio will remain constant. So Kc value will remain constant. So catalyst will increase the rate of forward reaction. Let's suppose x times. It will also increase the rate of backward reaction x times. So overall the rate of forward reaction will be equal to rate of backward reaction. Okay, the formation of product will be more, and simultaneously formation of reactant will also be more. So overall change will be constant. So Kc value will remain the constant, my dear friends. Let's go to the another point here. So let's talk about now equilibrium constant for backward reaction is inverse of equilibrium constant for forward reaction. We have already done it, my dear friends, that equilibrium constant for forward reaction is inverse of equilibrium constant for backward reaction. This relationship we have read. But it's only possible when the molar concentration in terms of forward reaction and in terms of backward reaction will remain the same. Okay, if you represent a reaction in forward direction and attain the equilibrium, and then you represent the same reaction in backward direction and attain the equilibrium, yes, then Kc will be inversely proportional to Kc dash, or Kc dash is inversely proportional to Kc, whatever it may be. But if the molar concentrations of the reactants and products are same, if they are changing, then according to that you have to either square the equations or you have to take the cube of the equations and make them equal. But relationship will be always inverse between the equilibrium constant for forward reaction and equilibrium constant for the backward reaction. Okay, let's go further. Now look here, my dear friends, equilibrium constant is temperature dependent. That means the equilibrium constant will have a fixed value or specific value at a particular temperature. Okay, I will write down for a given reaction Kc will have a specific value. So if I take on, my dear friends, this one, the fourth point, equilibrium constant is temperature dependent. So remember, for a given reaction Kc will have a specific value at specific temperature. So remember that term. Now, if I change the temperature, what will happen to the value of Kc? The Kc value will also change for the same reaction. If you carry out a particular reaction at a specific temperature, the Kc value will be something fixed. Kc value will be fixed. But if you change the temperature, the Kc value will also change. So for a given reaction, Kc will have a specific value at specific temperature. So I will write down here, if temperature is changed, then Kc value also changes. Okay? And remember, you may think that Kc is a constant. You may think that Kc is a constant. Obviously it's a constant. Then somebody may tell me that why does Kc value change if it's a constant? Let me tell you, my dear friends, I am telling you, if you carry out any chemical reaction at temperature T, let us suppose, then Kc value for that reaction will be, let us suppose, X, and it's constant. But if you carry out the same reaction at temperature T1, as I know, now for this same reaction, Kc value is, let us suppose, X1, and that's constant. If you carry out the same chemical reaction at temperature T2, yes, now Kc value for the reaction will be what? X2. So if Kc value is X2 and that X2 is constant at that particular temperature, so Kc value will be constant with respect to a specific temperature. When temperature was T, Kc value for reaction was, let us suppose, X. When temperature was T1 for the same reaction, Kc value was X1 and that is constant. Okay, at that temperature. When temperature was T2, the Kc value is X2 and which is constant at that temperature, my dear friends. So I hope you have understood that point as well. Let us go further. Equilibrium constant is independent of initial concentration of reactants and products, my dear friends. I told you, the equilibrium constant only depends upon the concentration of reactants and products at equilibrium. So the concentration of reactants and products which are present at equilibrium, the Kc value will depend upon that. Kc value will not depend upon the concentration of reactant and product, okay, which are present at initial stage of the reaction. That means, usually you know that at initial stage, yes, reactants are 100%, but products are what? 0. So reaction has not reached to equilibrium at initial state. That means you cannot take the Kc value at the initial state. That means Kc value does not depend upon the initial concentration of reactants and products. But Kc value only depends upon the concentration of reactants and products at equilibrium, not at initial state. You know that at initial state, reactants are 100% and products are 0, my dear friends. I hope you have understood all these things, dear friends. So please remember them and make a note of it. Dear friends, let us see some applications of equilibrium constant. The first one is predicting extent of reaction. Second point is predicting the direction of reaction. And the third point is calculation of equilibrium concentrations. So let us take them one by one. Dear students, let's look into the first application of equilibrium constant, which is predicting extent of reaction. Okay, so let us start, okay, with case number 1. If Kc value, which is basically the equilibrium constant, is greater than 10 raised power 3, obviously, which is 1000. If it is greater than 1000, then at that time products predominate over reactants, which means here, my dear friends, products will be, molar concentration of products will be very, very large than the molar concentration of reactants. So who are greater? Products are more than reactants when Kc value is greater than 10 raised power 3. Okay, so we know that Kc value is greater than 10 raised power 3. That means it's a very large value. The reaction proceeds nearly to completion. When products are more, when products are very large, then it's a very simple thing that reaction has taken place to large extent. Because when reactants will change into products, obviously the chemical reaction takes place. Yes, when more and more reactants are changing into products, then the concentration of reactants will keep on decreasing, and concentration of products will keep on increasing. So now we have large number of products as compared to reactants. That means more amount of reactants have already changed into products. and which means that the reaction proceeds nearly to completion. That means the reaction has reached near to completion but not completed. Because if reaction completes 100%, then equilibrium is not possible. So reaction has reached near to completion, where most of the reactants have changed into products, but not 100%. Yes or no, my dear friends? So obviously I will tell here the reaction, okay, has taken place to greater extent or large extent in case number 1, when Kc value is greater than 10 raised power 3. Look at this reaction, okay? Reactants are changing into products, and obviously in this particular reaction HBr will be very large and these two reactants will be very small concentration, because you can see here Kc value is 5.4 into 10 raised power 18. That means here also the reactants HBr will be far greater than H2 and Br2. That means most of the H2 and Br2 have reacted and they have already changed it into what? HBr. And finally at the end equilibrium has reached, my dear friends. So here the products will predominate the reactants. So the reaction has taken place to a large extent. So in simple terminology I will tell molar concentration of HBr will be far greater than molar concentration of H2 and molar concentration of Br2. Correct? So let us go further in case number 2. If Kc value is less than 10 raised power minus 3, then what happens? 10 raised power minus 3 means 0.001. Okay, my dear friends? So if Kc value is less than 0.001, then at that time reactants predominate over products. So in this case reactants are far greater than products. So when reactants are more, products are less. That means less amount of reactants have changed into products. Okay? Reactants in this case are more. What is the meaning? The meaning is that reactants do not want to change into products. That's why they are more. Here the products were more. Yes? That means reactants have easily changed into products. So products were predominating the reactants. But in second case, when Kc value is less than 10 raised power minus 3, that is 0.001, what happens? The reactants are more than products. We found at equilibrium, reactants are more than products. What's the meaning? Meaning is simple. Because Kc value is taken at equilibrium only. So reactants are more than products at equilibrium, which means reactants do not want to change into products. That means reaction will take place to a large extent or small extent, a very small extent. Very small extent. Because at equilibrium reactants are far greater than products. They do not want to change easily into the products. That means, we will write down here in case number 2, reaction has taken place to a very small extent. And in this case, if you look here, Kc value is very small, the reaction rarely proceeds. What is the meaning of rarely proceeds? The meaning is very simple. It has taken place to a very small extent, my dear friends. And let's take an example of this. N2O2 and 2 times NO. In this case, my dear friends, these two will be greater than what? NO. The concentration of these two reactants will be greater than the concentration of NO. Where? At equilibrium. Are you following my point? So at equilibrium, N2 and O2 concentrations will be far greater than concentration of NO, nitric oxide. Because this reaction has taken place to a smaller extent. Okay? So remember, my dear friends, in first case equilibrium was established when reaction has taken place to a large extent. But in second case equilibrium was established when reaction has taken place to a small extent. Here the products are predominating the reactants. Yes, because it's taking place to a large extent. And here the reactants are more than products. That means reactants are predominating the products. Yes, here the equilibrium will establish it. Okay, after the reaction has reached to a large completion. Here the equilibrium will establish it very fast. Why? Because a small amount of reactant will change into the product actually here. So let's look into the case number 3. third. But before looking into it, have a look here. Kc value. Kc value is here 4.8 into 10 raised power minus 31. And that is less than, okay, 10 raised power minus 3. So obviously, my dear friends, what happens? The reaction here at this particular point has taken place to a very, very small extent, or rarely. So now look at the case number 3. If now the Kc value is in the range between 10 raised power minus 3 to 10 raised power 3, what is the meaning? If now Kc value has a range, let's decide that range, 10 raised power minus 3 and 10 raised power 3, that is 0.001 and that is 1000. So my dear friends, the Kc value between 0.001 and 1000, if you look here, okay? So the Kc value in range of 10 raised power minus 3 to 10 raised power 3, then the appreciable amount of reactants and products are present. What is the meaning of that? Here in this case, reactants and products are present in good amount. So both are present, both reactants are written here, both reactants and products are present in good amount. Here products are more, here reactants are more, and here reactants and products both are present in appreciable amount, means good amount. Good amount of reactants, good amount of products, but don't tell they are equal. Reactant products are not equal. Good amount of reactants and good amount of products. First case, products are more, large. Second case, reactants are large. Third case, reactants and products are present in appreciable amount, means good amount. When Kc value is between 0.001 and 1000. Okay? Now look here, take this chemical reaction, H2 and I2 gives me HI. So here in this particular case, product and the reactants both are present in good amount, appreciable amount. And the value of Kc is 57. And you know that 57 will come between them. So my dear friends, 57 will come between 0.001 and 1000. And at this point, what will happen? Both reactants and products will be present in a better amount. So now we can extend, we can easily tell whether reaction has taken place to a large extent or small extent, okay, or to an appreciable extent. In first case, when Kc value was greater than 1000 at that time, products were more than reactants, which means reaction has taken place to a large extent or nearly to completion, okay. In second case, we have seen when Kc value is less than 10 raised power minus 3. At that time, reactants were more than products at equilibrium. So when reactants were more than products, understand that reactants do not want to change into products easily. That means reactants are predominating the products. So reaction has taken place rarely, or it has taken place to a very, very small extent. And finally, we have Kc value. If Kc value is between 0.001 and 1000, or between 10 to the power minus 3 and 10 to the power 3, at that time what happens? The reactants and products will be present in an appreciable amount. That means the reaction has taken place to an appreciable extent. Large extent, very, very small extent, and appreciable extent. I hope you can easily tell now, based on Kc value, whether reaction has taken place to a large extent, or very, very small extent, or appreciable extent. Okay, please make note of this. Dear students, let's understand the second application of equilibrium constant, which is predicting the direction of reaction. Okay, whether the reaction goes forward, backwards, or it goes both forward and backward at the same time, which is equilibrium. So let us have a look here. Let us take on, first of all, a chemical reaction. N2 gaseous plus 3 times H2 gaseous gives me 2 times NH3 gaseous. This is just a forward reaction and there is no equilibrium established. So shall I tell that this is before equilibrium? Before equilibrium. Now, when the equilibrium has not been achieved, at that time I can take only Qc value. I have given you this idea in thermodynamics chapter also. I can take Qc for this reaction. Qc is equal to molar concentration of products raised power 2 divided by molar concentration of reactants raised power equal to their stoichiometric coefficients, my dear friends. So what is this QC? I have already told you this is reaction coefficient, my dear friends. So reaction coefficient is exactly similar to Kc, but there is a difference. QC is the molar concentration of products divided by molar concentration of reactants, but its value can be taken at any point of time during a chemical reaction. Correct or not? So I am taking the QC value before equilibrium, my dear friends. Can I take the Kc value for this? For this reaction, it's not at equilibrium, so Kc value cannot be taken. For this reaction, it is before equilibrium, not at equilibrium. So before equilibrium, I can take QC value, I can easily take, okay? But Kc value cannot be taken for this reaction because it has not achieved equilibrium. Now if I make this reaction to achieve equilibrium, my dear friends, in a closed system, N2 gaseous plus 3 times H2 gaseous will give me 2 times NH3 gaseous. So this is at equilibrium, my dear friends, at equilibrium. So what happens at equilibrium, my dear friends? Reactants are changing into products, products are changing into reactants. So again I can take QC value here, QC NH3 upon N2 into H2 raised power 3. This value can be taken, and even the Kc value can be also taken here, right out here. That is NH3 raised power 2 upon N2 into H2 raised power 3. So this can be taken here. So look here. Before equilibrium, my dear friends, when reaction was only moving in forward direction, at that time what I did, I could take the QC value. But Kc value is only taken at equilibrium. Okay, I will write down Kc value if I mention here. QC value can be calculated at any point of time. Okay? But if you look at the Kc value, my dear friends, Kc, equilibrium constant value, is only calculated at equilibrium. Calculated at equilibrium. So this reaction was not at equilibrium. So which value I calculated? QC. So QC is molar concentration of products divided by molar concentration of reactants. Correct? At any point of time. I cannot calculate Kc for this reaction because this reaction is not at equilibrium. But look at this. This reaction is at equilibrium. When this reaction is at equilibrium, what happens? QC value I can calculate and Kc value also I can calculate, my dear friends. So here, now you have understood one thing, that it can be calculated at any point of time, QC. But Kc is only calculated at equilibrium, my dear friends. Please remember. So now let us understand the situation. If QC value is greater than Kc, yes, then reaction proceeds in backward direction. That means the products will change back into the reactants. That means there is a chance of the product changing back into the reactant at that time. So it is proceeding in the backward direction, my dear friends. So this is our backward reaction. So when QC is greater than Kc, then backward reaction will take place. Products will change back into reactants. Look here, if QC is greater than Kc, my dear friends, I wrote here QC is greater than Kc and here it should be QC less than Kc. If QC is less than Kc, then reaction proceeds in forward direction. What is the meaning of this? A very simple terminology is here. In second case, I will tell you, QC value is less than Kc value. So reaction proceeds in forward direction. That means here reactant will change into the product. That is the forward reaction will take place. Correct? Now case number 3, if QC is equal to Kc, then reaction is at equilibrium. That means here the reactants will change into products, products will also change back into the reactants. So now when QC value is greater than Kc value, at that time products will change back into reactants, that is backward reaction will take place. So backward reaction takes place. Products can change into reactants. When QC value is less than KC, at that time reactants will change into products. When QC value is equal to KC, reactants will change into products, products will change back into reactants. So now my dear friends, you have understood that these three things, and you have also understood the direction of reaction. Here it is a reverse reaction, backward reaction. Here it is forward reaction, and here it is both forward and backward reaction. So this was about how QC and KC relationship can determine the direction of a particular chemical reaction. So please have a look and make note of this.